Let's analyze the motion of this Nerf soccer ball by creating a motion diagram. A motion diagram is an analytical tool for determining the positions, displacements, average velocities, and average accelerations of the object whose motion we wish to understand. Consider the motion of this tossed ball after it's been released. The ball travels in an arc. We track the motion of the ball as it moves through the air, frame by frame. It's important to note that the time interval between any two adjacent frames is constant. The trail of dots that track the ball form the heart of the motion diagram. Each dot represents the position of the ball at a specific moment in time. So here is a motion diagram of a tossed ball, very much like the Nerf soccer ball that we tossed in front of Victor's Lament. It's very much like the motion diagram that we developed using Vernier's Lager Pro, except it doesn't have as many moments in time for the ball. So it's got fewer dots than the Vernier Lager Pro analysis had. But other than that, it is qualitatively the same. And I'll be using this smaller set of dots motion diagram to develop the rest of the things that go into a motion diagram, because it'll be easier for me to complete everything. So we've gotten to the point where we tracked the motion of the soccer ball through time, and at equal intervals of time, we put a dot where the position of the ball is as we move forward in time. And now we need to put the next element into the motion diagram. And the next element is the displacement of the soccer ball in each interval of time. So we need to represent this displacement of the soccer ball through time. And the way we're going to do that is by drawing an arrow between every two dots. And so between every two positions of the soccer ball, we're going to draw an arrow, and that arrow is going to represent the displacement of the soccer ball over that interval of time. And so let's put our first arrow in. And so this first green arrow represents the displacement of the soccer ball between the moment where it's at that first blue dot and the moment where it's at that second blue dot. So this is the displacement of the ball over that interval. And then we're just going to continue to do that for the rest of the intervals in the diagram. So then we have another arrow for the next displacement, next displacement, next displacement, and finally the last displacement. Now, maybe we want to label these to make it clear to the observer, reader, what these green arrows are representing. So let's label the displacements. So here I've labeled the first displacement delta R0, the second one delta R1, all the way through delta R4. Now, to take the next step in making the motion diagram, I want to go from thinking of these green arrows as displacements to thinking of the green arrows as being average velocities. But I can't do that without teaching you a little bit more about vectors, because these displacements, the displacement of the soccer ball between these moments in time, is a vector quantity. So you need to learn a little bit about what you can do with vector quantities before you're justified in thinking about these as average velocities. So we need an aside. We're going to have an aside regarding vectors. So let's consider an arbitrary vector. We'll call it A. Now, vectors have two main properties. They have a magnitude and they have a direction. And that's why representing vectors with arrows is such a reasonable idea. Here, this vector A is represented by an arrow. That arrow has a length, which is representing the magnitude of the vector A, and it has a direction. So for the magnitude, here we have vector A. Let's say in some unit system, A is 5 units long. So here I've noted that A is 5 units long, and I have to also note what its direction is. So we need some reference direction, let's say horizontal. Let's say that this little line segment that's pointing horizontally is pointing in the positive x direction. Then you could say that A is at a 45-degree angle counterclockwise from the positive x direction. Now you've specified this vector. You've said that it has this length 5 and this angle, 45 degrees from horizontal. And in fact, you could think of translating this vector anywhere you want. You could move it to the left or to the right, but it still has to always be 5 units long and always point in the same direction. All right, so we're getting there. We've talked about the two main properties of a vector, that is that it has a magnitude and it has a direction. Another thing you can do to vectors is you can multiply a vector by a number, a scalar, we call it. So you can multiply a vector a by 2, or you can multiply a vector a by, say, 1/2. Equivalent to multiplying a vector a by 1/2 would be dividing a vector a by 2, right? Think of dividing a by 2 or multiplying a by 1/2, it's the same thing. If we did that, if we took this vector a and we divided it by 2, we would wind up with a vector that is half as long. So it was 5 units. Now it's going to be only 2.5 units. But notice that it still points in the same direction it pointed in before. So this is an important thing to realize we can do to a vector, because this will allow us to make the connection between a displacement and an average velocity. This is because the average velocity is defined to be the displacement divided by a time interval delta t. And here you're taking a vector, a displacement, and you're dividing it by just a number, a scalar, delta t. And it's because of this formula that I had to teach you that this is an okay thing to do with vectors. And now you hopefully know enough about vectors to understand that these delta t's will scale the magnitudes of the displacements, but they won't change the directions of them. And since every displacement is going to be divided by the same delta t, that is, for every displacement in my motion diagram, there's the same interval of time for that displacement. All the displacements get scaled the same amount, so they all change in the same way. And so all of the velocities can be represented by the same arrows that were representing the displacements. So we were thinking, this was our motion diagram up until now. We had the blue dots representing positions, the green arrows representing displacements, and now we can make this change and think of these green arrows as being average velocities. So instead of delta R naught, I can think of V naught and V1, V2, V3, V4. Now, the one thing about this is that you really, in many motion diagrams, you don't need to label each velocity individually. You do in other kinds of diagrams need to label each velocity individually, but maybe not so much in a motion diagram. And so you could, for example, just represent all of these velocities with one symbol, maybe down at the beginning, just say V, and the reader should understand that this V refers to all of these green arrows for all of these velocities. All right. So now we've been able to represent average velocity on our motion diagram, and we really only have one kinematic quantity left to talk about and to include on our motion diagram. That quantity is the average acceleration, and we define the average acceleration to be a final velocity minus an initial velocity divided by delta t. But these velocities are, again, vectors, and I have not yet taught you how to subtract one vector from another, so you can't understand average acceleration in terms of this difference of two velocities until I teach you how to subtract two vectors. In order to teach you how to subtract two vectors, I really need to teach you how to add two vectors, because subtraction is very close to addition. So we need another aside. We need another aside to discuss vectors. So here, I want to teach you how to add two vectors graphically. Let's say I have a vector A, it's shown here, and I have a vector B, shown there, and I want to take B and add it to A. The procedure for doing this graphically is I slide B so that the tail of B is placed at the tip of A, and then the tip of B is going to be important. So I slide B so that the tail of B is at the tip of A. Then the sum, the vector sum of A plus B, is then represented by a vector that starts at the tail of A and goes to the tip of B. So C is a vector that is equal to the sum of A and B, starts at the tail of A, goes to the tip of B. Now that we've done that, we can actually figure out subtraction very easily. All we have to do is think of subtraction as the addition of one vector and the negative of another vector. So we want to think about subtracting two vectors, do the operation A minus B. So we're going to think about that as a minus b being equal to a plus negative b, which it is, right? So all you need to know then is how to get negative b from b, but that's very easy. To get negative b from b, you simply reverse the direction of b. And now I can add the way I just taught you. I can take negative b, I can slide it so that the tail of negative b is at the tip of a, and now the result, c, which is equal to a minus b, is going to start at the tail of a and go to the tip of negative b. And that's how you find the difference between two vectors. We are going to use this in our motion diagrams to complete our motion diagram. So here's where we left off in our motion diagram. We had positions in blue, those blue dots. We had the green average velocities. And now we're going to find or estimate the average acceleration by taking the difference of two velocities and dividing by the time. Actually, everything scales again, so we're not going to worry about this delta t, since that's just going to scale the length of everything. All we're going to worry about is the difference between any two velocities, and really not just any two velocities. If I want to know the acceleration at this second blue dot. So let's say this second blue dot is the position of the ball at this moment in time, at the second position of the ball that's known. If I want to know the acceleration of the ball at that moment of time, I should take the velocity after that moment in time, subtract the velocity before that moment in time, and the difference of those two velocities is going to be proportional to the acceleration at this moment in time. So let's do that operation. We take the final velocity. You see, I just took this second green arrow, which represents the second velocity, and I take the negative of the previous velocity and add it to it. So I flip the previous velocity so that I'm getting the negative of it, and I add that to the final velocity, and then the sum of those two vectors represents the difference of the final velocity minus the initial velocity. And so that's going to be represented by this red arrow. And so now I can take this red arrow representing the average acceleration at the moment the ball is at the location of this second dot. And I can just slide this red vector over, this acceleration vector over, to show myself what the acceleration is of the ball at this moment. Okay, if that wasn't completely crystal clear to you, let's try to find the acceleration for the next moment in time where I have a position. So at this next position, I want to take the velocity right after that moment in time. I want to take the negative of the velocity at the moment before, at the interval before that moment in time. I want to add v final plus negative v initial, which is the same as v final minus v initial, and I'll get the acceleration at this next blue dot. Okay, so I take the final velocity, and now I'm going to add to that the negative of the initial velocity. So now I have the negative of the initial velocity, and the sum of those two is the difference between the final velocity and the initial velocity. So that's going to be this red arrow. And now I slide that arrow over to what is the third point I have, the third position I have information about. And now I have an estimate for the acceleration at that point in time. But notice, I have an arrow for the previous moment in time that represents the acceleration there that looks exactly like the arrow I just made for the next moments in time acceleration. These accelerations look equal. And in fact, for a tossed ball under normal circumstances, they would be equal. The acceleration would actually be constant for a tossed ball. And that's what we're seeing from analyzing this motion diagram. Okay, well, let's try it one more time just so you get used to it. We are going to the 1, 2, 3, 4th position here. We want to find the acceleration at that point in time. So we take the velocity just after. We subtract the velocity before. And we take the difference, which is the sum of the final velocity and the negative of the initial velocity. And that difference is my estimate of the acceleration, which again is an arrow that looks exactly the same as the other two arrows. It's the same length as the other two arrows, and it points in the same direction. And so again, I'm getting evidence that the acceleration for a thrown ball, the vector acceleration for a thrown ball, is constant. And it is. Okay, so one last time, we take for the final point that we can find an acceleration for. Notice, because of the way we do these accelerations, you cannot find an acceleration for the first position that you have in time. And you can't find an acceleration for the last position you have in time because you don't have a v final to figure out the acceleration at the final point, and you don't have a v initial to figure out the acceleration at the initial point. So you can only use the other points in the motion diagram to estimate the acceleration. So let's do the last one that we can do. That's for this 1, 2, 3, 4, fifth point. And so we're going to take the final velocity. We're going to add the negative of the initial velocity. We're going to get an acceleration that's the same as it was a moment ago. We slide that vector over to the point in space where we have that acceleration. And now, actually, we have a completed motion diagram. This motion diagram has it all. It has the positions of the tossed ball. It has the displacements of the tossed ball, and those displacements can also be thought of as average velocities of the tossed ball. And it has the average acceleration of the ball over most of the moments that we know the ball's trajectory. So that's pretty cool. You can see what an incredibly powerful tool a motion diagram is to help you with all of these kinematic quantities. And to summarize, let's summarize these kinematic quantities that we've now introduced through the study of motion diagrams. We have position, we have displacement, we have average velocity, and we have average acceleration. And the notation we often use for these is position is a vector r, displacement might be a vector delta r, average velocity might be notated with v_av, and average acceleration might have the notation a_av. And so this summarizes everything we just did with motion diagrams, which is a whole lot. We did a whole lot with them. Okay, so that's maybe enough for now.